We're asked to find the area, the shaded area in this diagram, and we've got the curve, and we're also told about a normal. And actually, yeah, we're asked to show that this is the exact area. Okay, well, that's something to aim towards then. So I'm going to split this into two parts. I've got R1, which is going to be above the y-axis, and then I've got this little triangle, which I'm going to say is region 2, R2, below. Okay, so I can make a good start by doing an integral of the function between 0 and pi over 4. And actually, I should have just said that this is going to be R1. Okay, now this is a seemingly awkward looking integral, but sometimes when they look really awkward, they're actually some of the easiest to solve because you just have to kind of spot the rule that's going on. And if you look at the bottom and you find the derivative, it is very much related to the top. And what I'm hinting towards is that it seems to be in the form f dash x over f of x. And the integral of that is ln of the modulus of f of x. I'm not really going to go into details why. I mean, oh, the result is that when you differentiate, I'm going to go into detail why, aren't I? Because when you differentiate ln f of x, you use the chain rule, and you get 1 over f of x, and then you times by the derivative, so f dash x. So if you can spot it, if you can spot this kind of little idea in one of these integrals, then you're sorted. So when I differentiate the bottom, I'm going to get, well, the 3 is going to disappear, and I'm going to get minus 2 cos 2x. So I haven't quite got it in the right form, actually. What I think I'm going to need to do is take out a factor of minus 2 from that 4. And then I can write minus 2 at the top here. So that's still 4 cos 2x when I then multiply it back through at the end. Sometimes you can also do this like with a trial function, but I don't know, I quite like doing it this way. Okay, so it's now in the right, yes, in the right form. So I can straight away write down that this is minus 2. Okay, it's a definite integral. And then, like we said before, it's going to be ln of the bottom. So ln 3 minus sine 2x. Okay, so that's going to be minus 2. And then it's going to be ln 3 minus sine of pi over 2, which is actually equal to 1. You can put that in your calculator first. So actually I'm going to get ln 2. I'm just going to go straight for it. I hope I've explained that sufficiently. Ln 2. Got the modulus sign around it. I'm not going to even need that. And then I'm going to minus ln of the modulus of 3 minus sine of 0. And that is actually 0. So I'm just going to get ln 3. So I get minus 2 ln 2 over 3. And I can actually bring that power up. So it's ln 2 over 3 to the minus 2. And to deal with this, you basically, the minus means you swap it around. So it's going to be ln 3 over 2 squared. And then we're going to get ln 9 over 4. Okay, and that is a good start because we can already see we've got that term there on the left. So that's got to be correct, you know. And then all I need to now focus on is R2 and getting the term on the right. Let me just add that if you don't like what I did here, then you could expand it to make it minus 2 ln 2 plus 2 ln 3. And then you could actually factorize the 2 out and write it as ln 3 minus ln 2. It's just kind of a way of dealing with the negative a little bit in a slightly different way. We're going to get the same answer, but yeah, just wanted to make that comment. Right, now we're asked about, well, sorry, now we need to work out R2, and that's to do with the normal of the curve. Okay, for the normal of the curve, we need to remember that this normal is perpendicular to the tangent of the curve. So actually, we need to find the gradient of the tangent, and that means we actually need to find dy by dx. So there's quite a lot going on here because we have a fraction. Now, the thing about differentiating is whenever you have a fraction, you're basically going to be using the quotient rule. When you're integrating, it's not always certain what you're going to do. But yeah, differentiating, that is one thing it's set. So y equals 4 cos 2x over 3 minus sine 2x. This is going to be a u, and this is going to be v, and then dy by dx is actually equal to u dash v minus u v dash all over v squared. Right, well, I haven't found u dash yet, have I? Or v dash, so maybe I jumped ahead a little bit, but we can do that now. So u dash is going to be minus 8 sine 2x. I've used the chain rule here, but I've kind of done we call it like, sometimes it's called the outside inside rule. So basically, forget about the 4. I've differentiated the outside, so that's cos of something. That gives me minus sine, and it remains as minus sine 2x. And I times by the derivative of the inside, so that's why I've times by 2 to give minus 8 sine 2x. I'm not going to go into any more detail on that. And then for v dash, the 3 differentiates to 0, and then minus sine 2x is going to become minus 2 cos 2x for similar reasons. So dy by dx is then, oh, this is awkward, isn't it? Minus 8 sine 2x multiplied by 3 minus sine 2x. That's actually just the first term. And then I'm minusing u, which is 4 cos 2x times by v dash, which is minus 2 cos 2x. I'm going to change that to a plus 2 cos 2x. Just be really careful when you're writing it down to not, go back and check it maybe. I'm half expecting the answer to be not too bad when I then find the gradient, but we'll see. Then it's 3 minus sine 2x all squared. So that is the instantaneous gradient of the curve. We want to work out the gradient of the normal. So the first thing to do is work out the gradient of the tangent, which is the same as the gradient of the curve at x equals pi over 4. Now we could quite possibly do this without a calculator, but you know what? Let's play it safe and just put it in as a big fraction. Forget about that negative. Right, so we're working in radians. So always little check. As soon as you start differentiating, integrating, it's always implied to be radians. You can take some little shortcuts, like I've got pi 2 times pi over 4, so I can just say pi over 2. Okay, sorry, I'm a bit slow, but it's a bit harder on a computer. Hey, there we go. Right, and at the bottom, okay, again, I'm just replacing all my 2x's by pi over 2. And then I need to close the bracket again and then square it. Okay, so this can happen. And what I forgot to do is put a bracket there. I can see it. Minus 4. Okay. real life example of when you can make a mistake. The fact that I've got -4 is quite good, I think. I'm quite happy with that. But the thing is, if you don't get the 1 over 128 pi squared at the end, then you know you've done something wrong and you have to look back through. So that is the tangent gradient. So gradient of the normal is going to be the negative reciprocal. 1 over 4. And that's good, isn't it? You can see it's positive on the diagram, and it's going to be drawn reasonably accurately, I think. So we've got the gradient. Right, so next thing to do is to work out that equation um, of the normal. So y minus y1 is equal to mx minus x1. That's our general point gradient form. And we know it goes through pi over 4 zeros. So it's going to be y minus 0 is equal to 1/4 x minus pi over 4, which gives y equals 1/4 x minus pi over 16, in fact. And you could then integrate that straight line, but you don't need to. Because we've got a triangle, we can just say this is minus pi over 16. And so we basically got the height of the triangle. And we've got the base. R2 is going to be 1/2 times the base, which is pi over 4, times the height. Forget about the negative. Remember, we're looking at a positive area. Pi over 16. You need to make sure you put all of this in because this is a show that question. But actually, if you put it in your calculator, you'll then get pi squared over 128, which is all we need. So we've got this area for the R2, and we've got the blue area, ln 9 over 4. So hence, maybe I'll just write R1 plus R2 equals ln 9 over 4 plus pi squared over 128. So I kind of crossed through part of the answer, but look, I'm happy with that. Okay, well done. Really good question, I think, and I hope you enjoyed it.